So the first assignment for today's class would be the class we had last, where we used Boston data sets, which I'm still going to use today, of course. We made a prediction that day. We did the training and we did plotting. So what you're going to use now is that what you're going to do after now, and you're going to submit is you will make a prediction with that model. So what that means is that you just pick some random stuff like a house. You want to predict what will be the price of this particular house based on one or two things or based on some features. So I expect you to do some research on your own. So asking about using the model you have already built. That when you say model you've built, that means the code you have already written that we trained with. Sorry, I'm having a calling. Hello, Tochi. I can get a call. I'm getting a call from you.
No, it's not me. It's my father.
Okay. Okay, I've responded. I think I never knew he sent me a message. Okay. So what I'm saying is this, you will research on your own. We have built a model, meaning that we have trained an algorithm with the data set. We have seen the performance using some metrics. We have even seen the plot. I shared those plots with you last week. That was our focus last week. Or I think, yeah, last week. So what I'm saying now is that you will use that model we trained. That is housing price. I think it's this one. Housing price prediction. This is a model. Housing price prediction using Boston data sets. So what you're going to do now, you're going to make predictions using the model to predict the price of different houses. You could pick, let's use four houses, different houses based on parameters that they have. You're going to make prediction of what their price will be. So you predict. Please do read some stuff online about it and see what you can do with that. Okay, so for today, we did do our training on the last, which I want to show you here. The model we used for our training the other time was linear regression. So we use linear regression. So today, I want us to do something else. We are using a model called decision tree. So if possible, we're going to use random forest as well to do the training. Basically, they will all be the same, other than the fact that we'll be changing. So you take note of this. We'll be changing this model from sklearn.linear_model import. Here we use linear regression. So for the next one we want to do now, so we'll be using import decision tree regressor and plot tree. So you'll be seeing the variations. So just follow and try as much as possible. So here I call it housing price prediction using decision tree. Let's see. Or posting data set. Cool. So let's see how we go from there. So the basic thing remain. So we're going to do the import. So you can type along with me because by this time now you should be comfortable with this. So from numpy to import numpy as np import speeding. matplotlib.pyplots as PLT. And so we're using Boston dataset still. So here we import the Boston dataset. And how do we do that? We say from sklearn dot dataset. So here we're going to import this fetch openml, fetch underscore openml. So let me see what this gives us. Okay. So this, so far, they're not different from what you knew from the last class. So this place now, I want to import the machine learning tools we'll be using. What we'll be using, so we're going to use from sklearn dot model underscore selection. So what do we normally use that for? Model underscore selection. You import what?
Train testing.
Thank you, train test. Yeah, I love that. You import train test plate. So from sklearn dot model underscore selection. So we import train test slips. So where we split our data set into training set and to our testing set. Okay. So the next thing is again from sklearn dot tree. Now that this is a different bit of module. It's still sklearn, but instead of, because we're using decision tree, so decision tree works on tree, like the name, decision tree, making different trees to make predictions. So we'll be importing a new model that we've not used before, this decision tree. So to be, I think we've used it some times ago, but for this Boston data set, we've not used it. So to be sklearn.tree. So tree is that model in sklearn library. So here we'll be importing this tree regressor, and also be importing plots underscore tree. Okay. Then we'll be using some metrics. Again, it's from sklearn. So what do we use to import metrics? Metrics. So from sklearn.metrics. So we'll be import mean underscore squared error. I explained some mathematical basis behind this last class. So we import mean absolute error, and we'll be importing R2 score. So this will be the metrics that we use to judge if our model has done well or not. sklearn, this is learn. Okay. So far so good. So the next thing would be, let's start. So we have got the tools needed. We've got the data set we need. We've got the metrics we'll be using. We've got the basic libraries we'll be using. So let's try and do something then. So the next one would be to make predictions or to draw a training first. So let me go to the second stage now, or I call it next step. So here I say, okay, maybe I should have them together. So what I want to do here is load. I want to load and explore the real data set. So how do we do this? So boosting, just like the other time, boosting is assigned to, so you're going to use fetch underscore open ML that we already imported. Open ML, that's a method, and we'll call it on name. So our name is boosting. Boosting, and it takes version. So it takes version, that's version 1. Okay, so that's to load. Thereafter, we want to create a data set or a data frame. Create a data with a feature data. So how do we do this? So since I showed us the other time that the raw boosting data set needs to be cleaned up and needs to be prepared. For instance, let me show us again. I showed us that data. For instance, if you call boosting, if you print boosting, for instance, so let's see what we're going to have. So by printing boosting, you can see the way it appears. It appears in a data frame. I mean, sorry, not in a data frame structure, but it appears in array. So that's why you see in dictionary format. So you have data and you have the headings. So this, you can work with this satisfactorily. So you need to make it that's the target we want to achieve here. So let me just, so that's why we need to create a data frame with the feature data, and that will be what will make sense for us. Let me write this note. This output, the output from this call is not clean enough for our training purpose. So this is not clean enough for our training purpose. And that is why we need to create a data frame. So how do we create a data frame? You also know about that. So let's just call it, let's call the object data. We call PD dot, you know by now, is called data frame, and you call it on boosting that we've already created. So but boosting takes boosting dot data. Okay. So that's how it's structured, boosting dot data. So this will create for you, it will create a data frame for you. I need to, let me put off this one for the sake of the class, so everything does not look rowdy. Okay, so now we have created a data frame, and that data frame is saved or is in a container called, or is having a label data. So then I also showed us the other time that this data set, the way it's arranged is that it has the X data, the feature, like, let me run this again. If you look at this, it says we have 506 rows, 13 columns. So what are the features we have here? We have cream, zen, induce. I've explained all this means. So you see in all of these columns, there is no price column. There is no price column. So all of them are just feature column. And we know that for us to do a fine job, for us to predict or for us to train, we need to have a price column. So that's the essence of doing what we want to do now. And what is it we want to do? Let me silence this again, comment it out. So what is we want to do now? We want to also create price data. So what we're going to do is that we will use there is boosting.data. So this is how it works. There is boosting.data. There is boosting.target. Boosting.data. So this one will load the features, while boosting.target will load the price or the sorry, this will load the features here. So boosting.target will load the targets here. The target, or in this case now, that will be the prices. Okay, so that we've got the boosting.data. This will load for us the data, which is the X part. Then boosting.target will load for us the prediction part. That is the price. That's what we want to use to make our predictions. I believe that makes sense.
Yes,
Do let
sir.
me know. Okay. Do let me know if there is confusion. Okay.
No.
How do we do that? What we need to do now is to create. I want to do something, and what I want to do is to add a new column to my data, and I'm going to call that column price. And this is how to do it in Pandas. So this is already existing. Data is already existing. A data frame called data is already existing. Now I want to add a new price to it. You can add many columns to an existing data frame. So the way to add it is you will index that data by the name you want to add to it, by the new column you want to add to it. So here now the name is price. I want to have price. And what is going to happen is what I'm going to call on this is the boosting.target. So this boosting.target is what contains the price. And that's what I'm going to pass into this data frame I'm creating, this new column I'm creating. So what price does is to create a room. So boosting.target will fill it up. This like buying shares, and the other things you need inside the room. So this is the house or the room is price. That's the column. Now you need to pass in boosting.target into it. And when we do that, we will be able to create a new column. But of course, it's a string, so you need to tag it up. So let's run this. And you compare this. Now let's print data. Print data. You see the data would have changed from what it used to be. I'm sure you knew before there was no price there. But now you see price. Can you see? So this is a new column that we just added, price. So for you to be sure that that's what we actually added, let's say we call this one Nigeria. You see, this is the new column we're adding. And this new column, we fill it up with boosting.target. So in this, when we fetch open ML and we passed in this boosting argument, so it's what fetch for us that data set. But that data set exists in two forms. We have the data, boosting.data, then the boosting.target. Boosting.data contains the features, boosting.target contains the price. Hold on, please. Okay, so boosting.data saves the price, so it saves the features, while boosting.target helps us to know the values of the prices. Okay, so and that's why you can see that there is a difference between this print data, what this data contains, and the first one we did when we printed boosting. So they are even this one, they are boosting, which is also this. So they are different now. Okay. So the next thing now will be, let me take this out also, because I don't want everything to be cramped up. As we read it, you can see. So let me just add this note. This contains the new, sorry, I still put Nigeria. This contains the new column price. Just add it. Okay. Now that we've done that, again, you can always check the shape, the number of features. So you can always check those things up. But for us, we already passed that one. You can also check describe. So let me just run this one for us. So I want to do data.describe. Okay. And I want it to print. So this is the data.describe. This is what it gives to me. So it gives us the information about the data. So you can see how it's cleaned up. So the count for this first column is 506. So every column has entry of 506 up until price. And the mean, so the describe it just give us the statistical analysis or the statistical breakdown of the data set. So here it has calculated the mean for us. So for the cream column, the mean value is 3.61 for the Zen column. So this will give us information that the mean price is 22.53. The standard deviation, that means how apart are these deviated from the mean. So here 8.6 and so these are just basic information, statistical information about this data set. You can see the maximum price, the maximum value of the price is 50K. The minimum is 5K. So we have a variation between 5 minimum to 50 maximum. Then the 25% of the data set for the price, the 25% of it falls to 17,000. The 50% fall within 21.2, 75% fall within 25. The maximum value is 50K. Okay, so let's do some data preparation. So to do some data preparation, now I need to do, maybe I should just, let me leave this as it is, at least for you to know the output of describe. So what I want to do now is I want to check on I want to prepare data because we need to train a machine learning model. You can open. So here I say prepare data. Prepare the data for ML training. So how do we do this? Of course, we need X data. So for X data, actually, if I had not added price, if I had not added this price, this is our X. You remember I said this contains only the features. So, but we have added price, and the reason was just to show how to add. But normally we shouldn't have added because price is already, boosting the target is already containing price range, price values. So we could have just called it the Y, but there's no problem with that. So it's also for you to know how to manipulate data sets. So here now what we're going to do is, for us to get our data for X data, I'm going to drop the price side. So it will be X, data.drop. And what am I going to drop? I will drop the price. I'll drop price. And I need to show where is the price, which axis is the price. I said axis 0 is the row, axis 1 is column. For ND array, if you do 2D array, so your 2 dimensions, so it can only be 0 and 1, 0 and 1. But if I'm dealing with 3D array, so you'll be having 0, 1, 2. But for this class, it's going to be 0 and 1. That is 0. Axis of 0 will be axis 0 will be row. But we're not dropping row, we're dropping column. Is a column we just added, the price column that we're dropping, because that price should not be part of the feature, which is the X data. So we don't need that. So we're going to drop 1, axis 1. That means this price belongs to a column. So that's the meaning of this. So it will drop price. And you need to tell the program which axis is it? Is if you put 0, you're going to have an error. Let's try that. If you put 0 here, it will tell you there is nothing like that. So price not found in axis. That means it's telling you that this price is not found in 0 axis, which is row. And of course, that is correct because row is not the place where price belongs. It belongs to column, and column is 1. So now we have done that. So we have got X now. So to do the Y, so X is usually used as a capital letter X because it's a matrix. Y, what do you mean by matrix? As I've shown us before, you can see this is a matrix that lines by rows, line by rows. So you can see price is not matrix, it's just a singular, it's just a series of number. So we call that scalar. You just call it just series of numbers, numeric, just a series of numbers like that. Okay, so Y is used as, is always represented as small letter. And how do we get its own? We also do, actually there are 2 ways we can do it here. We can call data, we can call do, you see that we do boosting, will be fine also to call boosting dot target. But here, to use this one, we need to convert it to a data frame. But we don't need that since we already have a compacted data set or data frame where we have added price. So since we have dropped price, so all we just need to do for this one is just to call on data again and index our data with price. So it means we'll be using price for the Y. That's the prediction part. Okay. Now that we have done that, I also explained to us the need to convert to float type or to convert to machine learning type. Because if you should check the information about this data set, for instance, if you check it, you will see that, like we did the other time, we will see that some numbers are not floats. So I think that day we have like two number categories that are not floats. But for us to work with machine learning and train our model properly, we need to convert to float. So here I say convert to float type. How do we convert to float type? Very simple. Just call on your X again. X, which is the feature data. So what do you call it? Just say X dot as type. X dot as type. Use as type to convert from one to the other, from one data type to another. So as type, and for this as type is float. So you are using float. Then Y as well. All you just need to do again is to say Y. Did you say something? Is somebody speaking? Why? Oh, okay. Thank you. Any problem? Okay, so let's run this. Now we got our X that is in float, we got a Y that is in float. So I've converted. The next thing is we want to split the data and want to split the training into, split the data into training and into testing. Okay, here. So split data into training and testing set. Okay, so how do we do this splitting? You already know that for a long time, X underscore train, Y underscore train. Sorry, let's do it X train, X underscore test, Y underscore train, Y underscore test. Okay, and that will be assigned to, so we call train test split that we already loaded. Train underscore test underscore split. We already loaded that, so let's call on it now. I'm passing this argument. So let me split this to So we're gonna have XY, and also let's have test size. So the test size will take the ratio test size 0.2. Is someone speaking? Okay, so this should be common. For every argument you are passing, you need to separate them by a comma. Random state. For reproducibility, random state. Here you use a 42, just random underscore state. Okay. Now that's done, you can also check your size, but I'm not for that now. You can check the shape of each one and check what is it. But that's not what I want to do now. Now the next thing I want us to do is we're going to try different depth. There's something called depth in training and using decision tree. That means how deep should your trees be? Like what it means that how many questions should I be asking? To what level should I go down in my questioning? So again, I don't want to bother you with the mathematical framework behind this, but just know that decision trees or those tree related algorithms, they use something called depth. And this depth just means, in a simple way, how deep should my questions be? Because decision tree is about asking questions. So I want to know this thing is this. So what are the questions I need to be asking for me to be able to make decision that actually this is what it is? So then how deep, or like how many layers should I go in this informing the trees of asking these questions? Okay, so just take it like that we use something called maximum depth. And for this maximum depth, we want to see how each perform. So what I'm going to do here, I want to show some stuff here. And I want also to use decision tree with different depths, and you will see something. So here I want to train decision trees with different depths. Decision tree. I'm making. So decision trees with different depths. So how do we do this? Now let me help to do this. You say print. Rows complex. Okay. What controls complexity?
Orange. But not orange.
Don't worry, I'm going to explain what this does. Small depths. So
You know what I do? Yeah, I don't.
yeah. Okay, so just hold on for me. I'm trying to do a setting. I will explain this. So I want to test a different maximum depth, and I will also explain that. As I said, this is a new part today, so we want to test different max depths. So max depth will be, so let me create a list of numbers. So I have 2, I have 3, I have 5, I have 10, I have 20. So using different depths, and I have none. So I have this list of depths. I will try with 2 depths. I'll try with 3 depths. I'll try with 5 depths. I'll try with 10, then 20, and no depths. So what do we have? So what we're going to have some results. So we need to instantiate a result with empty list. So what will happen is that for each of these, this result we're instantiating, you should remember this when we treated Python, when we treated conditional statements, loop for loop and even while loop in Python, we treated something like this. So we have created the list we want to use. Now the result is instantiated on 0. So the next thing is going to be that we're going to create a for loop statement. So we're going to say for max depth, or let's say for each, for you to understand, for each depth in where? Are you following? Thank you. For each depth in max depth. So what should I do? So here I need to create and train model. That's what I want to do here. Create and train model. So what will happen is that this model we want to train, we take 2 first, use it to train, enter result. You go back to 3, enter result, go back to 5, use it to train. So that's what we're setting up here. So we're saying we want you to use the looping function to do our training. So therefore take each depth, for each depth in max depths. So create and train model. So what will happen here is that we need to define the model. Define model. So here we say model is a, remember I said we're using decision tree regressor. That was what we imported earlier on. We imported decision tree regressor. So we're going to instantiate a model, or we're going to create an object of this class, decision tree regressor. Again, by now you should be much more familiar with this. So we call this class a model. We inherit everything that decision tree regressor is having. Somebody has already created decision tree regressor. We want to use it. So it's like we want to use what somebody has created. So that's all the simple thing we're doing here. But before you use this thing, you call you pass in some argument. For instance, max depth. So max depth is one of the arguments you want to use. But remember, you could have put a number here, maybe 2 or whatever. But because we'll be using different variations of max depth, so what we're going to tell our program is that, you know what, my max depth is, instead of putting a number, you remember what I talked about, add coding. So instead of me putting a number to my max depth, I just say use max depth. What this means is that when my model is using 2, so it will come here, you say, okay, max depth, what should it be? So at that instant, it will use 2. When it's done with 2, again, I said max depth is max depth. So when it's using 3, it will change this max depth to 3. When it's using 5, it will change this one to 5. When it's using 10, it will change this to 10. And to be doing that on and on and on and on until it's done. Then when you get to none, it will change it to none. So that's the cool thing about this. And here I have random underscore state. So for this random underscore state, you know, this one, you can just add code, it is 42. So, okay, sorry. This one will be each depth, not max depth. Sorry, it will be each depth. I hope you are right. I hope you understand what I'm doing here. I should have put each depth, not max depth, because each depth is what we have used here. So it will be each depth. That will be. So each depth is 2, each depth of 3, each depth of 5, each depth of 10, each depth of 20. Okay, so that's our model. We have created a model. We have instantiated an object model using decision tree regressor, and we have passed in this argument. So the next thing we need to do now is to fit our model. Let's fit the model. Model.fit. So this model.fit, as you know, is what we train our model. It's for training. Just a line, single line of code. And what it will take is, it will take X train and Y train. You remember? Again, I gave a simple formula. When you are training, you use X train, Y train. When you are testing, you use X test, Y test. When you are taking your metrics, you use Y prediction, your Y test and Y prediction. Is that okay? When you are fitting, okay, maybe I should just add it up again. I have said this before. Let me just add it. Remember, during training, which is fit, use X train, and that makes sense. So those one have train, the data that has train. So X train, Y train. That's one. Then during what? Testing. That's when you are making prediction. During prediction, use X test, Y test. Okay. During metric calculations, use Y test and Y predict. Okay, this should be fine. And that's what we're doing here. So for model fitting, we use model.fit and we take X train as an argument and Y train as an argument. Let's run this. Okay. So what is the error about? Name X train is not defined. So what happened? Why have we not defined X train, X test? Okay. X train. No. Okay, we didn't. I think we didn't run this.
We've not run.
Yeah, I think we didn't run it. Yeah, okay. So let's run it again now. Cool. So marks them. So this one just printed for us some information. So when you use small depth, so let me quickly explain what this means. Small depth is simple tree. Just like I'm asking you. So when you have an interview, and the interviewer just asks you 2 questions. How are you? What did you eat today? That's a simple question. It might be that the job they want to give you is a simple job, like cleaning. Because if I need to give you a management job, I will not just ask you 2 questions. So that is simple tree. And it may underfit. What's the meaning of underfitting? Underfitting means that when you train, okay, no, I will not tell you. There are 2, we call them there are 2 phenomena. There's one called underfitting, there's another one called overfitting. Please take time. Read about this also. Read it and send me the answer. What is the difference between underfitting and overfitting? And number 2, how I will still send the questions to you. How can we prevent underfitting and overfitting in machine learning? So I'll not tell you. So that will be a classwork for you. So there's overfit, there is underfit. So when you use small depth, there'll be underfitting. When we use large depth, there'll be overfitting. There might be overfitting. When we use none, so that might be, they'll be likely going to be overfit. So again, the assignment is go and read the difference between underfitting and overfitting. Please send it to. Okay, that's just a print statement, some print statement here. So the next thing, we have trained already. The training has happened. You can see just with one line of code, we have completed our training. So the next thing we want to do now is, I want us to do predictions. We train so you can predict. That's why you train. You train to check. When you are trained in the class, you are tested with examinations to check what you can do. That's a prediction. So we want to make predictions. And how do we do that? So here now we're making predictions. So to make prediction, I already gave you the formula. So white train, let's call it white train predict. You can call anything you like, the left-hand side. But for the right-hand side, you use predict, model.predict. So that's what you use. Prediction. To make your prediction, you use, sorry, I need to correct something. I need to correct something here. For prediction, you use for your prediction is, where's my prediction? During prediction, you use X test. It's X test, not a Y test. X test you use. Okay. So here, what I want to do is I want to do training prediction, and I want to do testing prediction. Now, please take note. Why am I making training prediction? Actually, it's not necessary. We are concerned much more with testing. But again, look at how I match them up. To make my training prediction, I use my X train. But the main one is the Y test prediction. Y test predict. So for my Y test predict, again, it's still the same model. Model does predict. And here now, what am I going to pass here? I'm going to pass in what? X test. So when you are making prediction, you use your X test to make your prediction. Next one. So the next thing we're going to do now is, let's calculate the matrix. Calculate the matrix for both train and test. So I'm making predictions for both train and test. So how do we implement this? Very simple also. You already have them done. So the first thing is, here I want to do the training, then I want to do the testing. So let's say train. So what are the metrics we've imported? We imported 1, 2, 3. We imported mean squared error. Mean squared error. Then we also imported mean absolute error and R2 score. If you remember, I told you that before you can actually get your, there's something called the root mean squared error. So that is the ID prediction. It gives you a better view of your prediction. If you watched last week video and even before now, you will get this better. And even I've even given the assignment on that. But the point is this: for us to know our root mean squared error, we need to know our mean squared error. So first of all, we check the mean squared error. We check the mean absolute error. Then we check the R2 error. And today we're going to be checking for the training and also for the testing. So let's take them one after the other. And to be very simple, just like I've told you, to be very, very simple. So let's see what happened now. So let me start with, I said we're going to be doing training and testing. So my training, how effective was it? Before I even check it with the test. So I said train, mean squared error. Mean squared error. I'm going to call in mean squared error matrix that I already imported. Mean squared error. I'm going to call it as a function. It's a function that somebody has built. We're just using it. And again, because we are doing training now, we are doing training part of it. So it will take Y train, and it also take Y train predict. See, it will take this Y train predict and Y train itself. So it's comparing training to training. Y train predict. Then the next one is so the other partner will be to do the test RMSE or test MSE rather. Test MSE. So this will just be the same thing. Mean squared error. And just like this, but the difference now will be that since we are dealing with test, so this will now be Y test, then it will also take Y test predict. Y test predict. Can you see now? So for this test, this MSE under the test matrix. So it's going to take mean squared error as a function that we have imported. Then you take this first argument, y test. Y test is the part we splitted when we splitted our data set by calling, where is that? This, when we call test size, is splitted to train and test. So that means the test size is 20% of the entire data set. It means the y test here is 20% of y train. I mean, of the entire y, The y train is the 80% of the entire y. So we also splitted x into 2080, meaning that the x train will be 80% of x, and it will be 20, the y test, the x test will be 20% of x. That's the meaning of what we're doing here. Okay. And by that, I have got y test and y test predicts. So this will give me the mean squared error. Okay. So that's for mean squared error. So let me tag this mean squared error. Okay. Then for the other ones also, the same principle, the same method. So let's say I want to also find the mean absolute error the same way. So if I want to find mean absolute error, since I've already imported it, the same thing I'm going to do. So if I want to get the train for mean absolute error, so again, I'm going to call it mean absolute error. Mean absolute error is a function, and I'm going to pass in two arguments again. For the train, I will pass in y train, y predict. Is that making sense, please?
So, yes, sir.
Test MAE for the test. So I'm also going to call mean. I've already imported this as a function. As a metric here. Mean absolute error. Here, I'll be passing into it, since I'm dealing with test. So I'll be passing to it y test and y test predict. So the next one, the third one, I imported three metrics. So the third matrix is R2 score. So for my R2 score, the same thing. So for train R2, so for train underscore R2, again, I'll be passing into it R2 score that I already imported. R2 score, I'll pass into it for training parts. I'll pass y train, y predict. Very simple. Just be repeating based on what you are doing. Then for test R2, again, I'll be passing in R2 score is a model. Is a function. But now I'll be passing in for test. I'll be passing in y test and y predict. Cool. And now that we have done that, let's run this again and be sure we're fine. So this has happened. The metrics have been calculated. That's why we have a success running. So the next thing now is we want to see that the statistics. What do we have as statistics? Please, I need you to open your mind. Please, I need you to open your mind. Okay? And I will. So let's see something. The next one is to get three statistics. Get three statistics. So here to get the statistics, we create a function, we create a variable called n leaves, n underscore leaves. That's number of leaves. We call model. So in model, there's a function called get. Can you see everything? Everything is existing. Get number of leaves. Get number of leaves. So there's a function that does that. So it means number of leaves is in model. You can get number of leaves because we have already trained a model on data decision tree regression. And when we run this, then there's something we want to do. You remember we did depth setup. So because here we're getting statistics, this is just for statistics. We just want to see how we perform, how our model perform actually. At this point, we can stop whatever we are doing because the training, we have already completed the training and we've got the matrix. All this one we're just doing is just to get statistics and to really see what really happened under the hood. We are done here. If you do here, you can, let me even show you something. From here, you can already know what your result is. Maybe I should even do that before I begin to go to this level. But the only thing is that it will help us have a better idea of something else. But from here, you can know what your, for instance, I can print, for instance, my absolute print, let's say my test MSc, for instance, print the test mean squared error is, okay, let him print for me the test MAE, the test mean squared error, okay, test MSE. Okay, let him print this for me. Let me hold on this one first. I just want to show you that we have really done all this time just to get statistics. We have already done the training here. Can you see? Can you see that we have done this metric? That means these are results for test mean squared error. Then I can edit it. I can say take it to 3, format it to 3 decimal places. Format this to 3 decimal places. You can see that's 10.416. So I can make it 2. Or let me leave it at 3. So you can see now the training has been completed. All I'm just doing now, after now, is just to see more about our model. So let me show you some other things that we can also show. So you can also repeat this for, this is for test. You can do for train also. The test, so here you can use it to, you can change this one to train, mean squared error is, and you change this one to train. Okay? So let's see this one too. Can you see now? The train mean squared error is 0. That's what we have. The train mean squared error is 0. And let's repeat the same for the other matrix. And that makes sense. You know, I will explain that to you. The train mean squared error is 0. I will explain why to you. And that's why I was telling you that we don't really need it. We need more of test. I will explain to you. Let's see other matrix. So I can also repeat for this one. I can copy this and repeat for the other matrix. So I can say the test mean absolute error is test mean AE, mean absolute error. And also I can say the train mean absolute error is, so I'm going to change this one to AE. And let's run that and see. Okay, so let's print empty here for space to be, and here. Can you see? The test mean absolute error is 2.394. The train mean absolute error is 0. So that means we have trained, and that's why we're having these metrics. Okay, now let me do something again. So I can repeat this also for R2 because we also have R2. So let me print empty here. I will print R2 score. So the test R2. The test R2 score is, okay. And this will be changed to test R2. Test R2. The train R2 score the train R2 score. So you change this also to train. Oh, I just need to change this one to R2. R2. Now, this one should be in percentage. First of all, let's run this. Can you see? The test R2 score is 85.085. Now R2 should be in percentage. So let's do something here. The test R2 score. So let's convert this to percentage. How do we do that? It's very simple. Just multiply this by 100 and make this a percent. Again, the same thing here. Multiply this by 100 and make this a percent. So let's run this and see. Cool. Can you see now? The R2 score is 85.796. Now, let me quickly remind you something. Did you remember our last result? Can anyone remind me? Okay. Let me show us. This was last time when we used linear regression. Are you following me?
Yes, sir.
Okay. When we used linear regression as a model, and we checked mean squared error, mean absolute error, and R2 score. See the results we got that day. For that, we got this. Where is our training output? Where is this? Cool. I think it's here. Yes. Can you see now? On this linear regression model, our mean squared error was 24.29. Our root mean squared error was 4.93. Our mean absolute error was 3.19. And our R squared error was 66. So just focus on this for now. 66.88, because this is like the accuracy of your system. Please take note. Here you have 66.88. And see what we're having here now. Using different model. What do we have here? 85. So which one is better?
This one.
This one is better. So that was what I was telling you, that you don't just say, I'm going to use a model for this. So it depends on what you are doing. So it means for this type of job, it means decision tree is a better model than logistic regression. And that is why our score, R2 score, has improved. Then if you look at the mean absolute error, the mean absolute error here was a 2.39. Then shows, let's compare for the other one. Mean absolute error here was 3.19. Of course, you know it's in thousand. So 3.19. This one is 3.19, while this one is 2.39. So there is a wide difference. Okay, and that thing is the test, the mean squared error. The mean squared error. Let's check the mean squared error for the other one. The mean squared error here was 24.29. 24.29. And see, the mean squared error here is 10.41. That is more than times 2. That's like 2.5. So it means in all ramifications, in all metrics of considerations, using Boston datasets, decision tree performs better than logistic regression. Okay, so I said I'm going to say something. I want to talk about this 0, 0 we got here. Now, this is what it means. Take note that it is training we are doing it for. What it shows is that your teacher has come to the class and he said, today, I want to give you 3 examples. The first example is 1 + 1 is equals to 2. You write it. The second example is 2 + 2 is equal to 4. You write it on the board. The third example is 4 + 4 is equal to 8. You write it on the board. And as everybody, it's time for exams. And he says, you can copy from the board. Just do the work. You are permitted to copy. Then he says, number 1, exam. 1 + 1 is equals to what? Number 2, example. 2 + 2 is equals to what? Number 3, exams. 4 + 4 is equals to what? And the same thing is on the board. And he says you can copy from the board. What do you think will happen? Do you think people will score 100, 100, or what? What do you think will happen to the performance?
100.
Yes. So that means there will be no error. It means nobody will miss anything. That's the meaning of this statement, of this result we have here. I don't know if you get that point. That's why we have this.
Yeah.
For training, the mean squared error is 0 because nobody is missing anything. Because I'm only copying what I've seen. So that's what happened here. So, and that's why I said initially that we don't need to do metrics for training, because all things should be equal. If I train you on 1 + 1, and again, I'm saying you can copy from the board, and I'm saying my exam to you is 1 + 1, then you should also get it. So it means you are not learning anything. That's the meaning. I'm not learning anything. So even though you have 0 here, you score no, you missed nothing, and your performance is 100%. That doesn't mean you are brilliant. It only means I've tested you on what I've trained you on. But it's a different ball game when the test is different. When I say 2 + 2 is 4, and I tell you that to actually get that you can't chew. And that's the exam, that's the test. Now my exams, and I say 3 + 3. So it's a different question. So that's why we have this result. So there's something else I want to add here, and is the idea of root mean squared. I told you before that root mean squared is a better version of measurement than mean square error. I explained that last week. You can go back to watch the video. So I'm not going to do the mathematical details again. I'm just going to do what needed to be done now. Now, to get root mean squared error, you will notice that there is no root mean squared error matrix here. There is none there. So, but what happened is that if I know mean squared error, I can actually get the root mean squared. So what's the meaning of that? This all I'm going to do to get this matrix. I'm going to say, where are you? So there's no much problem here. All I just need to do is saying, okay. Maybe I should include it. Where should I? Okay, let me include it here. Or better still, let me include it here. Train underscore root mean squared error. Train underscore root mean square error. So here you don't need to import anything. You just need to calculate numpy dot sqrt, that's square root. Just need to pass numpy, the square root of train MSE. So that's all you need to do. You just take the square root of train MSE, then test MSE. Again, you pass this numpy dot square root, and you pass in test underscore MSE. Okay. Now let's print it out now and see what we're going to have. So again, I'm going to copy this back. No, it's this one. So let me use this. I just edit it. I could also have copied that. So I'm going to copy here. Here. So I change this one to root mean squared error. Root mean squared error, and that will be train root mean squared. So that'll be train root mean squared, then train the test root mean squared. So let's run this and see what we have. Cool. And you can see for test root mean squared error, all I just need to do is to square. So if you square, for instance, 10.4, so this is what we're going to have. So that's the result here, 3.22. And for root mean square, of course, when you square 0, you're going to get 0. So 3.22. So let's compare this root mean squared error of 3.22. Let's compare it to the last version, root mean squared error. Can you see now? Root mean squared error is 4.93. So you can see. So this performance is still better. In all the metrics of measurement is better because it shows that decision tree is a better version of than linear regression here. So where linear regression is also good, it has its own good spots. But for this situation we are dealing with, making prediction of prices, this is okay. Now, if we end it up here, it's fine. But I just want to show us that there are more that can be done. And that's the idea I was trying to bring up here. I hope we are okay on this. So you can see that yes, we've seen what we are doing. We've seen our work. We've seen our performance. But I want us to go deeper. And that's why I'm saying, let's get some tree statistics. So to get some tree statistics, again, we've already got the number of leaves. And I'm going to explain that in a jiffy. So this depth of string, you're going to take this command, you take maximum depth. But you know, we're not using maximum depth, we're using each depth. We're using each depth. If each depth, else infinity, else sorry. Okay, I'll explain this to you. Okay. Now we want to get the results. Yeah. Where did I define? Okay. I need to go back to where I make my definition. Now, let me do something here. Because we are doing looping. So everything we are doing should be inside of this. So let me call this out. Let me call this out. I'll call this out and I'm trying to see the best way to undo this so for you to understand properly. Okay, I think I should create, let me see the best way for, okay. So for me, I think you've understood this one. So what I'm going to do here is, okay, I will come, let me reverse this. So for me, I'm going to do something now. And what I'm going to do is, again, I will now recopy this, no. I'm just looking at the best way not to confuse you guys. Okay. So this is like a new, so let me call it digging deep. Digging deep. Okay. So based on that, I think I'm safe like this and cool. So I call it digging deep. And for this digging deep, so I can now recreate this training because it has to be inside that loop for it to really perform what I want it to perform here. So I'm going to refer back to what is that? Where are you? So let me start from make predictions. Okay, I think I should call it from here, from make prediction. Okay. 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 Cool. So digging deep. So you can see I'm just repeating what I have before. Okay. Okay. So I think they're on the same. Cool. Okay. Yeah. We're there now. Now, the next thing is, you remember I've already instantiated results on 0. I've started counting 0. So just take note, all I'm doing is what I've done, but on a different level now because of this loop. So the loop is what makes the difference now. You already have the idea. You already seen how our model perform. So at least put that at the back of your mind and believe that you understand this part also I'm treating now. So I want to do result.append because for all this, each depth we have defined, there will be a result. And so we need to now append the result. We append whatever we are getting to the result. So I'm going to call it result.append, result.append. And here I'm going to pass a function. And that function will be, we create a dictionary list. For this dictionary list, something will happen. Results is results, not results. Results. So what will happen is that we're going to have key and can you see that dictionary is very important again? So you're going to have a max depth. So you're going to have max underscore depth. So that is a key. And it will take a value of depth string. Depth string. I'll explain. Don't be confused. Don't be just follow on. Then I'm going to have another key. I call it number of leaves. And this is a key. And we take a value of n underscore leaves that we've created. Again, I'm going to have train RMSC, train underscore RMSE. And that's the key. And this will take a value of train RMSE. Another key I need is train. I call it train R2. Train. I call it train underscore R2. And it takes a value of train R2. That's called R2. So we also have a test underscore R2. So that's a key. Of course, you can call this key anything you like, but the values are very important because you've already defined the values in your experiment or your running. So test R2 will be test underscore R2. We already defined this one. And there's a comma. Test underscore R2. That's test R2. Okay, we also have so we have RMSE, train RMSE. Oh, we need to also define test RMSE. Test underscore RMSE. That'll be test underscore RMSE. Okay, train RMSE, test RMSE, train R2, train R2, test R2, test R2. So what else do we measure? We measure train. Okay. Did we measure absolute? I think we measure absolute error. Okay.
Yes,
Test. Okay, thank you. Train underscore mean absolute error. And you take this train underscore MAE, right? And we do the same thing for the test. Test underscore MAE. We take test underscore MAE. Yeah, I think we are good on this. Test.
The test is
test. Okay, test MAE. Oh, cool. Then let's take the final one, overfit. So we need to calculate overfit too. So how do we calculate overfit? So overfit is you subtract train R2 from test R2. Okay. Yes. I think we are train underscore R2 minus test underscore R2. Yes, I think our dictionary is fine now. So don't worry, just follow, you will see. Let's run this first. Cool. Okay. Okay. Now, before I even explain further, let's see something first. Let me separate them. Let me kill this first. I mean, sorry, let me silence this part. Oh no. I think I've defined this again. I don't need that again. The test. Okay, let me take this out because I already transferred this down. Okay, cool. So I've already transferred this. So this is for this part. Now let me run this. Okay, so let's see some comparison here. Now see the first one. The test mean squared error is 25.993. The train mean squared error is this. The test absolute error is this. The train absolute error is this. Can you see something? Are you seeing something? See, the test R2 score is 64.55. At this point, the train is 70.49, 46. And here, we have the mean squared. We have the test mean squared error. So there should be a separation here. There's a place that is not separated. Where is that? 1, 2, 3. The test mean squared error. The train mean squared error, mean absolute error. Test R2 squared. Then okay. Yeah. But this is where I'm actually going. Can you see that at a point, our R2 score got to 99.365? I don't know if you saw that. Can you see at this point, our R2 score got to 965. Okay. Then let's say at the end point, the test R2 score at the end now ended at 85.796. So you can see that there are differences, variations along the training line. So I just want to point that one to you. And that's what we're trying to achieve. What we set up here gives room for that. But just hold on and see another thing. So I wanted to print for us now some information so we can see better what we're actually doing. So let me do something. Please don't be lost. Just try to follow this interesting part. So I've seen the results and we've appended. So we have seen different results. The first one we did, we just used a one-time result. But for this one now, we are seeing different results. And we'll be able to pick the best we be able to use. So let me do something. Let me ask you to print for us. Print this for us and tell me the depth. So take for me depth string is greater than okay. Trainer 2 is frame. Multiply by 100. And test R2. Let's multiply by 100. So. Okay. Let me see. Okay. Let me silence these prints that are they are making the work. Okay. Depth infinity. Okay, depth is infinity. Leaves is 386. Where is that? There should be a comma here. Okay. Okay. Okay, sir, sorry.
Is he done? Are you done?
Okay. So depth is infinity, leaves is 386, train R2 is 100, test R2 is this, then overfitting is this. Okay. Now let's convert this to this is a final result. So again, it's not different from what you have known. Okay. So let's convert it to data frame for us to see a better version and see something. So results now. So we've got results and we're going to call it, convert to data frame. I ask you to do print for me. So I want to do some comparison, and I call it comparison comparison of depths of different depths. So to do this, what it's going to do for us is it will do, let's do some kind of print again. And here we say, take this and multiply it by 80. So we can have a cool design. So this is just, I'm just designing it, nothing. So this is what I'm doing here now, comparison of different tree depths. That's what I've done with this code. Okay, but the read data frame now, how do we do the conversion to data frame? So very simple. All we just need to do is to make a print, or let's say print. And what we're going to print now is we want to convert the results underscore df. So results df convert to data frame. Sorry, this is, it should be results underscore data frame. So let's call on it pd dot data frame, and it will take the argument of results. Okay, so let me do something here. Let me just say print results. Results underscore df. So let's run this one and see what we have. Okay, cool and cool. See, this is what we have. Let me quickly explain this. We have this result. The final result, depth is infinity, leaves is 386, and this. But remember, we created the dictionary. This dictionary. So I want to explain that to you now. This dictionary has created this for us. See what is happening here. Maximum depth, number of leaves, train RMSE, test MSE, train R2, test R2, train MAE. So what does this mean? See something. These are the index 0, 1, 2, 5 to 5. When the maximum depth was 2, remember we created a maximum depth here. Maximum depth here, you remember? And we took a loop of for each depth in maximum depth. Now this is what is happening. Take note of this. You have 2, 3, 5, 10, 20, then none. That's what you have here. 2, 3, 5, 10, 20. This none is infinity, okay? Or none. Now, when the number of leaves for maximum depth of 2, the number of leaves was 4. For maximum depth of 3, the number of leaves was what? 8. For maximum depth of 5, the number of leaves was 25. For maximum depth of 10, the number of leaves was 191. For 20, it was 386. For none, it was 386. Now, that's one part. Now, let's now compare the results. So let me stay on R2. Let's use R2 to do the comparison. You will notice something here. See this test R2. Forget the train for now. Just focus on the test. For the test R2, for the maximum depth of 2, the test R2 was 64%. You remember? Multiply by 100. 64.
Yes, sir.
Then for the maximum depth of 3, it improved to 77. For maximum depth of 5, it increased to 88. For maximum depth of 10, our accuracy, that's the meaning of R2 in this kind of data set or this kind of use case, was 69. Do you notice something? When we were on 5 maximum depth, we had R2 of 88%. But when we were on 10, it dropped to 69. Can you see something now? Then it now peaked again. When we went to 20, it peaked back to 85. Then at infinity or none rather, it was 85. So what can we see here? There are kind of pattern here, but that's not all. You also need to look at the losses. For instance, look at the test root mean squared error. if you use the test root mean squared error here, you will notice that we have our lowest root mean squared error when the maximum depth was 5. That is when we have our lowest root mean squared error. And also, for mean absolute error, let's go to the test also. It was at index of 2, which is, index of 2, which is 5, maximum depth of 5. That was when we had our our mean absolute error. So our test mean absolute error was least here. So what can you say about this? If you want to choose a maximum depth, which one will you likely go for? Which one will you go for?
The 3.
The 3? What do you mean by 3?
The third option, that is 2.8.
2.8. This one?
Yeah.
Why?
Because it has the highest overfit.
Okay. You're talking about, you're using overfit here.
Mm-hmm.
Okay. But the highest, that's not, overfitting is not cool also. Overfitting is not good. The high number of overfitting. So you need to go for
overfit.
Thank you. It has to be what?
Low overfit.
Low overfit, yes. So which one is the lowest overfit in the model?
2.30.
2.30, which is this.
Mm-hmm.
And what does that correspond to? Maximum depth of what?
3.
Are you sure? Just check the index. This index 2.
Mm-hmm.
So check
2.
the maximum depth 2. What is that? That's there. It's 5. So this is index of 2. This is what is good for us. Mm-hmm. And when you compare it to where you have maximum depth, that is maximum depth of 5. Okay, so you're getting the idea. So let's do something now. So now that we have seen that, let's convert to something. I wanted to show something for us. I wanted to print for me results data frame. I want to convert to string and print to string. So I say results underscore data frame dot. There's a function called dot to string underscore to string. Then the index, I want my index to be false. That means I don't want to have index. So let's run this again and see what we have. Okay. So this is what we have now. This is what I want to produce. I want to produce something like this. Can you see that this final one, this is much more better formatted than this? So what the difference between this and this is just the formatting. Here you have the index number 0, 1, 2, 3, 4, 5, but here you don't have. So here you can compare just at a row. But see this one is splitted. That's why Tucci was having problem getting which one was 2.3, which maximum depth. But by looking at this makes more sense. So here you just see 5. You see the lowest is this, and when you look at the overfit, the lowest overfit is 0.03516. Now let's see the maximum depth that gives us the best results. So let's see something. Of course, you can see, you have already seen it, but let's write a code to print that. So let's tell the code to find the best depth for us. So find the best depth means we're looking at the highest test R2. So you could also use overfit. You could use a loss, but you just want to concentrate on IS. You have seen it visually. You have seen it's 5, but let's confirm it. Okay, so let's do something this way and say best IDX is so it will go to result. The result we have created, result underscore df that we just created, it will index it and locate test R2. You know, we have many columns there, so it will pick test R2 column. So we can change it to a different form. So it will go to test R2 and take this ID max. So that's how to check for the highest number, IDX max, and you call it, is a function, you call it on it. Okay, that's one. Then you also do so for the max depth. So let's run this first. So let's say print okay. The best IDX is R2 of 2. Test R2. Test R2, test R2, the max, maximum depth of 2. Sorry. Best depth string. Best depth string. Results underscore df. The results look, so to locate press underscore idx, then you take the maximum depth.
Yeah.
That's one. Okay. Maximum depth. Best IDX, max depth, then best depth is max depth. That's the best. Which fish? Best depth. Okay. To what is that? Max depth. Okay. Best max depths. And you see now it has confirmed what we actually saw. So best max depth is 5. So here we have best IDX. How did you get our best depth? Our best depth is to index the maximum depth and find the best IDX. So, and that gave us this 5, which we also confirmed. So the next thing, which will be the final thing, and I think it's better we put it to another time. So what we're going to do now, the next now is going to be that we will not train the model. Now that we have seen that the best maximum depth is 5, we now train the model with that 5 value and see what we have. But we've already spent a lot of time, so I need to stop it here. I'll encourage you to go through the video again and see how interesting this is. But again, you could see that in the training, we already achieved all that we needed to achieve before. So all this one was just statistical checks and creating a kind of results overview of the entire training. So we're going to call it a day here. Thank you so much for joining the class today. We'll see next time. Okay?
Okay.
Thank you.
Thank you, sir.
So please don't forget the homework. I'm going to send it to you, and